Good morning. Hope everybody's doing okay. As usual, we'll wait a second, 30 seconds or so, a minute or so for other people to join us. If you're here, please say hi. Today we're going to be talking about solutions and mixture. Solutions and mixtures, probably just the solutions parts today. Hi, Monica. Hi, Alyssa. Wait another minute or so. Hello, Joey. So before we get started on new stuff, good morning, Maria. Are there questions or things that you specifically want to go over today from previous things or whatever? Let me know if there are. Some other announcements. Hopefully you saw on Blackboard that lab is also moved online this Wednesday for section B04. There was another positive case. As you know, cases are going up all around this area. Plus, for us, we're chemistry for the health sciences, so I know a lot of you are working in healthcare fields, which makes you a little bit more vulnerable to being exposed. So we plan for all this. That's why we have these online options, and hopefully we'll be back in the lab before the end of the semester. We'll see. Yeah, we can definitely do a mastering chemistry problem. And which chart from the last handout? The one at the end with the. We can definitely look at that too. This chart. All right. I'm gonna pull up mastering chemistry also. So give me a minute or so. So when you say this week for the mastering chemistry, you mean solutions and mixtures, right? Joey. Okay. Yeah, we'll take a look at that. The online gas lab, there isn't a separate online gas lab. So the gas law stuff was all incorporated into the other part of the lab because it's all online. So what we would have done is we would have done the fat extraction part in person and the gas laws part as the online lab. Now it's just all in the same lump. So you just do that all together. Oh, and we did find one mistake. I think Monica found it. There is no part C in the online report about the bell jar that's described in the instructions. It's actually part F. So for some reason the piece got moved to the wrong spot. So it's later on down the page in part F if you're looking for that. All right, we'll start over with this review from last time. We'll finish up this table. So to look at the rest of the molecules here, CHCl3, that's going to be a tetrahedral. That molecule is called chloroform, by the way. So that'll be a tetrahedral type molecule like this. And that is covalent. In fact, all of these are. It has some polar bonds in the CCl bonds, and overall it's polar. It cannot do hydrogen bonding because there's no HO, HF, or HN bonds. So the strongest forces here are going to be the dipolar forces because it does have that dipole. All right, for N2O, we've got this structure. Oh, sorry, that's an O2. N2O is NNO. There's a couple different ways you can draw it with double bonds or triple bonds. Those are called resonance forms. We didn't really get into that. But if your structure is a little bit different, it might still be okay. That is covalent. That has one polar bond in the NO, and then it's not offset on the other side. So the molecule is polar, no hydrogen, so no hydrogen bonding there. So that is also dipolar. And then BF3 is kind of a weird one. You probably have to look this one up. It's actually trigonal planar, and boron does not have a full octet in this structure because boron just doesn't have enough electrons. So that one has polar bonds between the B and the F, but because it's trigonal planar, they all cancel each other out. So you've got like this way, this way, this way. Anytime you have a totally symmetric molecule like that with all the same types of bonds, the polarities usually cancel each other out. Again, no hydrogen there, so no hydrogen bonding. And this one's going to have primarily dispersion forces as we look at it here. In reality, there's some other stuff that goes on with BF3 that changes that a little bit, but from our principles here, that's what you would expect. If you said dipolar forces here, I think that's sort of okay as well because there are these strongly polar bonds. So recognizing that does make some sense there. Okay. So with the mastering chemistry, I'm going to pull it up here so we have it. I'm not going to go over it right away because let's go through some of the stuff first because it may make a little more sense once we actually get to that part in the packet here. But I will get to it at the end, and if I don't, you can remind me. All right, so this section, this is going to be our last section before the exam next week. We will, because of the way the schedule is set up, we will do a little bit of new material next week along with the exam, but it won't be on the exam. So you'll have a little more time to do the homework and digest it and all of that after the exam is done. But this is the last one that will be on the exam. So, oh, am I not coming through clearly today? My connection looks okay. Is which one dipole or H bond? Can anybody confirm that? Am I coming through clearly or am I cutting off regularly here? So this is how that, let me move this up here. This is how the bottom of that table should look then. So these last three, we've got dipole, dipole, and dispersion forces, maybe also dipole, but not hydrogen bonding because in order for hydrogen bonding, you need HO, HN, or HF bonds. So HF, HN, those can hydrogen bond, but the other ones cannot. All right, thanks for the reports. It looks clear right now, but let me know if it gets to the point that you can't understand. Yeah, the last one has to be um, either dispersion, or you could make an argument for dipole forces because of the BF polar bonds. But in the whole molecule, those dipoles actually cancel each other out. So the overall molecule ends up actually being polar. Okay, good. All right, let's talk about solutions and mixtures. So quick review of what we've been just talking about. Electronegativity increases, right, as you go to the right and as you go up. So as you're going up toward fluorine, which is the most electronegative element. And then we've got some different kinds of what we call intramolecular forces. So the things that hold the molecule together inside the molecule would be ionic bonds, so two ions getting attracted together. Then also polar covalent bonds, which we've talked about, and nonpolar covalent bonds. And so remember, we can split this up into metals and nonmetals to try to figure that out. So that's all kind of review from stuff we've talked about before, but it comes in again now because now we're talking about what happens when these things mix together. And the kind of shorthand statement for that, which you may have heard before, is like dissolves like. But we want to be a little bit careful with that phrase. When we talk about like dissolves like, it's not just polar dissolves polar and nonpolar dissolves nonpolar. It's a good shorthand, but it really has to do with similar intermolecular forces. So if molecules have similar intermolecular forces, they will mix better than substances with different intermolecular forces. And that's really what's causing this. When you create a solution, you have to take two pure substances and mix them together. So that means the interactions, the intermolecular forces between the mixtures, between the two substances, has to be stronger than in their original self substances. Right? So if you have, so for example, oil and water. So let's express oil like this, which is just means lots of carbon and hydrogen. So oil molecules are made primarily of carbon and hydrogen, which is all nonpolar. And as we talked about in the last chapter, those nonpolar molecules can kind of attract each other, sometimes fairly strongly, through dispersion forces by lining up and attracting each other with those forces. And then water molecules, now we know, attract each other with these hydrogen bonds. Which are stronger than the dispersion forces for the size. But if we had large molecules like in oil, those dispersion forces actually end up getting pretty strong. So to create a mixture or a solution between oil and water, we have to break up all these dispersion force interactions. We have to break up all of these these hydrogen bonding forces, and then we have to mix them together. But when they're mixed together, they're not going to make any new forces really, because the dispersion forces in water are really small because of the small molecule, and there's no polarity in the oil, so there's no way for those to mix. There's no way for those to mix. So we have the situation where the substances would rather stay by themselves so they can have their good interactions here and here rather than mix together. So generally, if you have some nonpolar oil and some polar hydrogen bonding water, um, they're not they don't have the same types of polarities, so it makes sense that they don't really mix. And so we can use that to make some predictions about what would dissolve, what would be soluble in water, or what would not be soluble in water. So for example, copper 2 chloride, let's look at some ions. Copper 2 chloride would be CuCl2. But in water, when it dissolves, it's actually going to break up into copper 2 plus ions and chloride ions. And now you have this highly charged ions, positive and negative charged ions, that can interact with the water and be solvated. Remember in the last section we looked at these ion dipole forces. Look at that again. Where the water molecules can surround the ion because of the positive and negative attraction. And so those should be soluble in water because water can now dissolve those ions. All right. So what we're talking about here is making something called a solution. And we've used that term before. We've used solutions in lab. Solutions are homogeneous mixtures that are combined so finely that essentially they're down to the atomic or molecular level. And really, it's a pretty general definition of that homogeneous mixture that's combined evenly throughout. We also use a couple terms, the solute and the solvent. We often think of the solute as a solid and the solvent as a liquid, but that is not always true. So let's look at some examples here. Really, the definition is just the solute has the smaller amount and the solvent has the bigger amount. So here are all some different types of solutions. Salt water, sugar water, brass, bronze, vinegar, air, soda water, dental amalgam, the like silver fillings that you put in that they could put in your teeth. Not so commonly anymore, but still happens. So here's like these first couple are what we would, at least what I generally think of when I think of a solution. It's got a solid that's dissolved in a liquid, and water is a really good solvent. So we say the solid dissolved in the liquid makes the solution, and that's solid and liquid. But let's also take a look at some of these other ones. So you can take some zinc and you can mix it with copper. You have to melt them together, and you make something called brass, and that's a solution as well because those atoms are intermixed within that new network, and that's a solid in a solid solution. The only reason that zinc is the solute and copper is the solvent and not vice versa is because there's less zinc. If instead we mix some tin in with copper, we have bronze instead of brass. And if we put some acetic acid and some water, we have vinegar. So there's a liquid and liquid solution. One kind of strange thing that happens sometimes with liquid and liquid solutions is that water is such a just ubiquitous solvent, it's everywhere, that sometimes water is still considered the solvent even when there's less than the solute. So for example, if you look at alcohol concentrations in like liquors or something like that, they always say, oh, this is 12% alcohol by volume or 5% alcohol by volume. So that's volume of ethanol versus total volume of solution. And when that percentage gets up above 50, technically there's more ethanol than water in that solution, but it's still reported that way for consistency. So you can have a 56% ethanol in water solution that's technically the ethanol becomes the solvent, but we still call the water the solvent in that case. All right, you can also dissolve air, or you can dissolve gases in another gas. So so air is a good example of a gas in a gas solution. You've got oxygen, carbon dioxide, water, other gases dissolved in mostly nitrogen. That's what we consider air. You can dissolve gas in a liquid, like carbonated water. We've got carbon dioxide actually dissolved in the water. And then you can actually dissolve liquid and solid or solid and liquid, however you want to think about that. In this case, mercury, which is a liquid at room temperature, when it's mixed in with a bunch of silver, forms what's called dental amalgam. And that's a really kind of a weird one because the solute is liquid, the solvent is a solid, but you have to melt the solid to make the solution in the first place. And then when it kind of rehardens, you've got liquid essentially dissolved in the solid. So you've got mercury dissolved within that silver matrix. So lots of different ways to make solutions. All you need is a homogeneous mixture, one thing with the smaller component, one thing with the larger component, or many things with a smaller component, one thing with a larger component. So let's find the solute in these examples. If we've got 2 grams of sugar and 100 milliliters of water, then that sugar is our solute. 60 milliliters of ethanol and 30 milliliters of methanol. The methanol is the solute in the ethanol because there's less of it. 55 milliliters of water and 1.5 grams of sodium chloride, that's our solute. And then oxygen gas and nitrogen gas, the oxygen gas is the solute. Okay, You may have heard these terms before: electrolytes, strong, weak, or non-electrolytes. Normally we would do I, I don't have one here. I don't have the equipment for it at my house, but you can look up electrolyte light bulb demo. And what's going to happen there is an electrolyte is when an ionic compound dissolves in water and dissociates into its cation and anion. So like we showed with the sodium or with the copper chloride above, you have cations, you have separate cations and anions in solution. And because of that, that solution will then conduct electricity. So you can pass electricity through a saltwater solution, a sodium chloride and water solution, but you can't pass electricity through, say, really pure, like deionized water. So you can have three categories here: strong, weak, or non-electrolytes. Generally, ionic compounds, when dissolved in water, are going to make strong electrolytes, but some don't. And then if things don't make ions at all, we have what we call non-electrolytes. So, for example, is there an example? There is an example here. So a good example of this is sugar in water solution. So sugar, let's say glucose, although table sugar is sucrose, but let's just say glucose, C6H12O6. You can dissolve that in water, but that's not ionic, right? That's covalent: carbon, hydrogen, oxygen, all nonmetals. So that covalent compound is going to dissolve in water. I mean, you've seen sugar dissolve in water, right? And it is dissolved. It is forming a solution, but it's not an electrolyte because it didn't form any ions in solution. So it didn't form sodium, like sodium chloride dissolved would make sodium and chloride. Those would be ions, so that's an electrolyte. But glucose would not. So any kind of covalent compounds dissolved in water are generally not going to be electrolytes, whereas ionic compounds in water will usually be stronger electrolytes. And whether something is a strong or weak electrolyte is something that you have to really test. You can't just like look at a molecule and decide if it's going to be strong or weak. You can decide if it's going to be an electrolyte or not based on whether or not it's a covalent compound like this that's not going to break apart, but you can't really make the distinction between strong and weak electrolytes. Okay, some other solution definitions here. Solubility is the amount of solute that dissolves in a certain amount of solvent. So let's, imagine you've got a solute, you've got a solvent. You can keep putting solute into the solvent and it keeps dissolving, and then at some point it stops dissolving and it just falls to the bottom of the container. At that point, you have what's called a saturated solution. So up until then, you had an unsaturated solution. There's less than all the solute the solution can. And then once it gets to that point, it's called saturated. So for example, if you add one more crystal to an unsaturated solution, all it would do is dissolve. That one more crystal would dissolve because it's unsaturated and there's more room, you can say, for the solvent. You can hold more solvent. If you have a totally saturated solution that's got all the solute that the solution can hold, and you add one more crystal, it would just fall to the bottom of the container because no more solute can dissolve. You've hit the solubility limit, so any additional solute would just fall to the bottom of the container. Now, it's also possible to make something called a supersaturated solution, where you can very carefully actually get more solute in there than the solution is technically able to hold. And the way you do that, solubility changes with temperature. So if you have hot water or hot coffee, you can dissolve sugar in it better than cold coffee. So you can heat up whatever it is. You can heat up your solvent, and you can actually add more solute because the higher temperature will hold more solute. And then you can very, very carefully cool it down and essentially trap that extra solute in solution at a lower temperature. And then when you add more crystals to that solution, and I'll move this so you can see it. when you add one more crystal to a supersaturated solution, you will generally start growing. It'll actually grow bigger crystals from that. That's how things like rock candy are made. That's why when you're cooking with sugar at higher temperatures, like making candy, you have to be careful to get rid of the little crystals that form on the edge of the container, because they will ultimately start growing into that supersaturated solution as it cools. Okay, so here's a very busy graph about what happens to temperature, to solubility as temperature increases. So let's talk about it together a little bit. All right, so on the x-axis, our independent variable here is temperature. So we're looking at what happens when we, let's say, increase temperature. And then this is the solubility. So this, you'll notice this is written in grams of solute per 100 grams of water. So if we have 100 grams of water, how many grams of whatever substance can we put in before we make to make a saturated solution? So for example, let's take sodium chloride at, where is that clear? At 50 degrees. So right here. So at 50 degrees for sodium chloride, the solubility is, I don't know, let's call that 38 maybe, 38-ish. So that means you can put about 38 grams of sodium chloride in 100 grams of water and it will dissolve. Any more than that, and it'll just fall to the bottom of the container and won't dissolve. Notice that sodium chloride is, it has a pretty flat curve, which means as you heat up sodium chloride, its solubility doesn't change all that much. Like if you're trying to dissolve a bunch of salt in water, it really doesn't matter what temperature you're at. It's going to dissolve about the same. It increases a little bit with temperature, but mostly the same. Look at some of these other ones, though, that make a huge, huge difference. So like this one, potassium nitrate, as you heat this up, you have a massively different solubility. So potassium nitrate at 30 degrees, like right here, can hold about 40, let's say 47 grams of, or water, 100 grams of water at 30 degrees could hold about 47 grams of potassium nitrate. If we just up that 10 degrees, now we can hold like 60 some grams of potassium nitrate. So a big, big difference. The dotted lines here are for gases. Gases decrease their solubility with temperature. That's why like cold beverages can hold their carbonation better and be more carbonated, and then as something warms up, it kind of goes flat, because it can't hold as much gas in solution anymore. I don't think CO2 is on this list, but HCl gas, NH3, SO2, as you increase the temperature, you decrease the solubility of those gases. So that's what that graph is showing you. So for these questions here, all this is asking is, can you read that from the graph and then decide? So let's do a couple. How much potassium chlorate can dissolve in 100 grams of water at 80 degrees C? So we go to 80 degrees C, we find the potassium chlorate curve, which is this one right here. And at 80 degrees C, it looks like, oh, whoops, I circled the wrong one. We'll do that one too, but we're looking. At 80 degrees C, potassium chlorate is right here, which if I'm looking at the graph, looks like about 45. So that's how much potassium chlorate can dissolve in there. We can also, let's look at that next one. How much ammonium chloride can be dissolved in 400 grams of water at 90 degrees C? So now we've got a different amount, but let's see how we figure that out. We go to 90 degrees C and find our ammonium chloride, which is up here. So that tells us that about 65 grams or so of ammonium chloride can dissolve in 100 grams of water at 80 degrees C. So to get 400 grams, we have to multiply that by 4. So if we call that 65 grams we have to multiply that by 4 to get the actual. Oh, I'm at 80 instead of 90. Sorry. Thank you, Alyssa. Yes. So 90 would be here. I'm not reading my question, which is just over 70. So let's call that 71. Yeah, I'm at the wrong one. So there. That should be that one, right? Thank you, everybody. All right. And then let's do one of these saturated versus unsaturated ones. If 110 grams of Ki were dissolved in 100 grams of water at 10 degrees C, is the solution saturated, unsaturated, or supersaturated? So we got to find our Ki, which is not on the list. I think that's a typo. I think this is supposed to be KCl. Sorry about that. If 110 grams of KCl were dissolved at 10 degrees C, well, let's look at our KCl is right here. So at 10 degrees C, we've got about 30 grams per 100 grams of water. So if we had 110 grams, that would be way supersaturated. Really, really supersaturated. Maybe that was supposed to be Ki, because Ki is much more soluble in water than KCl. Can't quite answer that. We have to look up another one. All right. So the next thing we're going to talk about is how we measure the amount of solute dissolved in a specific amount of solution. To do that, we use a term called the concentration. And we've seen this in lab, last week. Remember, there were some different HCLs. There was like 1M HCl and 3M HCl and 6M HCl, and you had to make sure to get the right one. When you have a solution, it's not enough to just say like because solutions can be at different concentrations. There can be different amounts of solute in a given amount of that solution. All right, it looks like my connection's having issues again, so I'm going to stop for a second. All right, I am looking okay at the moment, but that doesn't mean it's not going to get bad again. Seems stable at the moment. All right, let's talk about concentration. There are various different ways to express concentration, but it always looks like amount of solute divided by amount of solution. So that's kind of the general way to express concentration. Amount of solute divided by the amount of solution. And the thing that is sometimes tricky about this, or that people sometimes forget, is the denominator is the amount of the solution, the total amount of the solution, not just the amount of solvent. So in solubility, we looked per 100 grams of solvent. But when we measure concentration, we're generally measuring per amount of total solution. So for example, if you want to do a mass percent, so what percent is the solute in the total solution? So let's say you had let's say 20 grams of sodium chloride, and then so you weigh out 20 grams of sodium chloride in a beaker, and then you keep adding water until the total gets to 100 grams. So you're not you're not adding 100 grams of water, you're actually adding 80 grams of water so that the total solution is 100 grams. So you'd have 20 grams of solute, 100 grams of solution, and that is a 20% solution. So am I out again? It looks okay from my end right now, but that doesn't mean it actually is okay. All right. Still, it's okay for now. Well, we'll go back and look at the video after it gets recorded, and if there's stuff missing, we'll redo it on Thursday, or we could even do extra like tomorrow or Friday if we need to. So let's see if we can look at these couple different measures of concentration. So mass percent is just a percentage with the mass of solute divided by the total mass of solution. Molarity is a special one for chemistry, very useful for chemistry because we often want to know how many moles of something we have for reactions. And that is the moles of solute divided by the liters of solution. So those are the basic definitions. Let's get into that a little bit more. Okay. So you added 20 grams of sodium chloride and 100 grams of water. What would the mass percent of the sodium chloride solution be? So the mass percent, which is written percent mass by mass, so mass of solute, mass of solution, is going to be that 20 grams of, well, let's use our significant figures, 20.0 grams of sodium chloride divided by the total mass of the solution. So 100 grams of water plus those 20 grams of NaCl, right? So the total mass of the solution goes on the bottom, not just the solvent. And then because we want to make that into a percent, we multiply by 100%, right? So then we have 20 divided by 120, and that gives us 16.7%. So we would describe this this solution as 16.7% by mass. All right. And the tricky thing about that is when you see these nice even numbers, 20 grams of this and 100 grams of water, you look at that and you kind of think, oh, well, that must be 20% solution. But it's not. It's a 16.7% solution by mass because we're talking about the total mass of the solution on the bottom, not just the mass of the solvent. All right. So now let's look at that same solution and see if we can figure out what's going on here. So we have 20 grams of sodium chloride, 100 grams of water. What would the molarity of the salt solution be? So we can, let's use a different color here. We have to take this grams. Remember that molarity, which is capital M, is moles of solute divided by liters of solution. So that means that we have to get our solute in moles, which in this case is 20.0 grams of lost my pen for a second there, of sodium chloride. We want to convert that from grams to moles, so we use the molar mass of sodium chloride, which I believe is like 65 or so, right? 58.4. No, not 65. . So we convert grams to moles. And we get 0.342 moles. So then to find the molarity, all we have to do is divide that by the volume of solution. But what happened here is we don't actually know the volume of solution. So even though we can look up the density of water and we can figure out how much water we have, once we add that sodium chloride to it, we're going to have a different solution with a different density. So we can't really tell what the volume is. So we can't find the molarity of this example because we don't know what the total volume is. So let's look at this again and look at how we could actually do that if it does make sense. So if we have a 0.5 liters of solution that contains 6 grams of NaOH. It's a trick question. It's a question without the answer, without an answer that we can provide without doing some more measurements or research. We could make that solution and figure out the volume, but the illustration here is that we don't want to use mass in our calculation of molarity because we just don't know we can't go back and forth without those measurements. So here's more what a proper molarity should look like in number 25. If we have a half liter of sodium hydroxide solution with 6 grams of sodium hydroxide in it, then we can say 6 grams of sodium hydroxide is 40 grams per mole. Which gives us 0.150 moles. And then to find the overall molarity, we're going to take the 0.150 moles of NaCl and divide it by the total mass of solution. .150 divided by 0.5 is 0.3, so 0.300. And the way we report molarity is with a big capital M that sometimes has a little bit of a loop on the bottom. Sometimes it's just a capital M. Either way is fine. So we have 0.3 molar solution, is how we would say that, a 0.3 molar solution of sodium hydroxide, which tells us that there are 0.3 moles of sodium hydroxide in every liter of that solution. So molarity can also be used as a conversion factor. 6 molar HCl means 6 moles per 1 liter. 63% by mass HCl means 63 grams. Oh, the grams is already there. Means 63 grams of HCl per 100 grams of solution. So sometimes it can be useful to think of the concentration as a conversion factor because it gives us a way to convert between volume and mass or volume and moles depending on the type of concentration we're thinking about. So here's an example of that. How many grams of KCl are needed to prepare 125 milliliters of a 0.720 molar KCl solution? So this sounds tricky, but this is really a conversion problem. We're taking an amount in milliliters, and we want to convert it to ultimately to grams of KCl. Our conversion gives us a way to go between liters and moles, and then moles to grams. Right, then we can go moles to grams after that. So that's going to look like this. I'll set it up all in one big line, but you can also just do this one step at a time. So we can take the milliliters and convert it to liters. And this is really the step that's going to be the new part. How do we go from liters to moles? So 125 milliliters, we're going to convert milliliters to liters, liters to moles, and then moles to grams. All right, we'll go back up and talk about number 23 also. So these conversion factors we know, 1,000 milliliters in a liter. And the grams per mole we get from the molar mass. So we look up the mass of potassium and of chloride, which is 74.6. All right, so then how do we convert moles and liters between moles, volume and moles? That's what we use our concentration for. We've got a molarity reported here, 0.720 molar, which tells us 0.720 moles per liter. So if we calculate this out, we cancel milliliters, we cancel liters, we cancel moles, and we end up with grams of KCl. And that's our answer. All right, let's go back up to number 23. Why can't we solve this? We can't solve it because we don't know the volume of the solution. All right, hold on a second. Hold that thought. I'll be right back. Okay, sorry, I'm back. Oh, maybe blurry. Camera got angry. I can fix that. All right, there we go. Okay, so why can't we know this? We don't know the volume of solution. We know the mass of water is 100 grams. And we can use the density to find that 100 grams of water is about 100 milliliters. But when we add the 20 grams of sodium chloride, we're not going to have exactly 100 milliliters anymore. Because even though we say that something dissolves, it still does take up some space. So 100 grams of water with 20 grams of sodium chloride in it is not going to be 100 milliliters total or 0.1 liters total. It's going to be a little more than that. And we don't know how much more without measuring it. I suppose we could look it up in some sort of a table and figure out what the volume or what the density of a 20% by mass sodium chloride solution is. We could do it that way. But we don't have enough information right here to actually solve that. That was the issue there. All right. Let's look at these other two together. So these are also ways that we can use concentration as a conversion factor to go between volume and mass or volume and moles. Again, 4 molar calcium chloride solution to provide 0.17 moles of calcium chloride. So this is where a molarity becomes so useful because let's say you're actually doing a reaction and you need a certain number of moles of calcium chloride, which you calculated from the chemical equations that you're doing, or for the reactions that you're doing. So to figure out how much calcium chloride you need in solution, we can just go 0.17 moles of calcium chloride. And then we want to go, instead of moles, we want liters. So moles to liters, that's again using the molarity. So the molarity is 4.0 moles per liter. So this will cancel moles and we'll go 0.17 divided by 4. which would be 0.0425 liters or 42.5 milliliters. So now we know if we have this bottle of 4 molar calcium chloride, and we've done some molar calculations based on the equations to find that we need 0.17 moles, then we know we just need to measure out 42.5 milliliters in our graduated cylinder, and that's the amount, that gives us the proper amount of calcium chloride. If we had a more dilute solution, we'd need more of it. If we had a more concentrated solution, we'd need less of it. I'll let you try this one, and we can come back to it next week. All right, let's look at this mastering chemistry problem. This is number 31, about preparing a solution from some stock solutions, maybe a this actually goes into the next section here, or goes in with the next section. So let me make an extra page here. All right, so this is the question. You are asked to prepare 230 milliliters of a 3% mass by volume morphine sulfate solution. You have 4 50 milliliter vials of morphine sulfate labeled as 50 milligrams per milliliter. How will you prepare the aqueous solution? All right. So this is actually something we're going to look at next time, this next formula or this next section, but I'll just give you a preview so that we can answer this question. Oh, the 2 decimal places in the last one? Yeah, I didn't follow those rules, did I? So if we reported it in liters, we would call that 0.04 liters. If we reported it in milliliters, we would call it 42.50 if we're reporting the answer to 2 decimal places. So either way with that, like that. All right, so in a little preview of next time, and you can tune out here if you don't want to look at it, but because the question was asked. To calculate dilution, we recognize that the amount of solute doesn't change when you dilute something. So when you dilute a concentrated solution, you're adding water, but you're not changing the amount of solute. So the concentration that you start with times the volume that you start with is always going to equal the concentration you end with times the volume that you end with, because you're always just adding more solute. What these are, concentration times volume, like moles per liter times liters, gives you moles. So when you multiply the concentration times the volume, you are you're simply what am I trying to say here? The result of that is the amount of solute. So whether that's grams or moles or milliliters or whatever, the concentration times the volume is always the amount of solute. And if the amount of solute doesn't change, but the concentration and the volume do change, that means that you're diluting something. You're adding water without changing solute. So in a question like this, if we want to prepare 23 milliliters of a 3% solution, and we have 4 50 milliliter vials labeled as 50 milligrams per milliliter, which is a well, let's okay. So grams per milliliter is percent. So the milligrams per milliliter, we need to make that into a percent. So 50 milligrams per milliliter equals 0.050 grams per milliliter, because there are 50 milligrams divided by 1,000 is 0.050 grams. So 0.050 grams per milliliter times 100% is 5 mass by volume. Right, 0.05 divided by 1 is 5%. So you have these 50 milliliter vials of a 5% solution, and you want to make instead a 3% solution. You want 230 milliliters. So what we're going to say here is, remember the initial concentration times the initial volume equals the final concentration times the final volume. So our initial concentration is 5%, and our initial volume is, we don't know. That's what we want to know. How much of that initial solution do we need? Our final volume given, or our final concentration given by the question is 3%, and our final volume is 230 milliliters. All right, so we do a little algebra and we solve for our initial volume. $138 milliliters. So that tells us that we need 138 milliliters of our more concentrated initial solution to make a 230 milliliters of a final diluted solution. So how would we do that? There's some other questions specifically in the mastering chemistry, but basically you take 2 of the vials, because it says you have 4 vials. So you take 2 of them, you dump those in, and then you got to measure just 38 milliliters of that last one, dump that in, and then fill with water up to the 230 milliliter mark, and then that would give you your final volume. So it would be 138 milliliters of the stock solution, and then an extra, what would that be? An extra 92 milliliters of water in this example. All right. We'll come back to this stuff when we talk more about dilutions on Thursday. As you're going through this, if you're following along or if you're coming back to it and you notice parts of the video are completely unintelligible and you want to go through some of that material again, please let me know, because we can either just do that on Thursday or we can schedule another time to do that. Otherwise, that's it for this morning. So just a couple things to keep in mind. There's no lab for section BO4 this week. Well, there is lab, but it's online. And hopefully we'll be back in lab in person next week, but who knows. Next week will be the second exam. It will be a similar format to the last one, but I am building it this time in Blackboard instead of Mastering Chemistry, because we had so many issues with people not being able to access the exam in Mastering Chemistry. I am still planning to also offer the option of a one-on-one oral exam if you want to try that too. But that'll be next week, so that's just coming up. This is the last material that will be on that exam. All right, I will keep trying to get caught up with grading and all of that also. And let me know if questions come up. So thanks, everybody. Sorry for the connection difficulties this morning. It looks like we're okay now, but I don't know what was going on. I will see you all Thursday, hopefully Thursday evening. Bye.